Hello everybody, welcome back to the Gregorius Maths video. And today, as we did before, we're going to be proving a result which isn't normally seen in the context of probability via probability. So last time we proved inclusion-exclusion. This time we're going to prove Cauchy-Schwarz. And I have a feeling as I go through my probability notes that this might not be the last video in the series talking about a probabilistic inequality. But I thought this was quite interesting. The fact that you can actually view Cauchy-Schwarz, which everybody thinks is a geometric thing, you can actually view it probabilistically, which I'd never seen before. So yeah, I thought I would make a video on it today. And so what's the statement? Well, the statement is, the probabilistic version is, given two random variables x and y, we have that the expected value, the absolute value of the expected value of xy is less than or equal to the square root of the expected value of x squared times by the square root of the absolute value of y squared, like so. And okay, first things first, let's actually prove this, and then we'll talk about how it relates to the regular Cauchy-Schwarz inequality. So, first of all, let's prove this. Firstly, if the expected value of y squared is equal to 0, then this means that, well, if the expected value of y squared is 0, that means that y must just be 0. So it must be 0 with probability 1. So the probability that y is 0 is just 1. And that in turn implies that the probability that xy is 0 is also just 1, since y is always 0. And so then you get 0 is less than or equal to 0, which is true. So that case is fine. Now, if e of the expected value of y squared is not equal to 1, then let's pick some real number t. Then we have that x minus ty all squared, it must be greater than or equal to 0, which implies that x squared minus, okay, so this is greater than 0, which means that the expected value of this thing is also greater than or equal to 0. And if we use the linearity of the expectation, i.e. that e of x plus y is just e of x plus e of y, then we can break this up as e of x squared plus, minus, I should say, 2t e of xy plus t squared e of y squared, like so. And that's greater than or equal to 0. And if we now view this as a quadratic in t, so I suppose we're picking some t that's not equal to 0. If we view this as a quadratic in t, then since this is greater than or equal to 0, this quadratic can't have two roots, and so its discriminant must be less than or equal to 0. So what does that mean? Well, what's the discriminant? Just b squared minus 4ac. So we just get e of xy all squared minus 4 e of xy all squared minus 4ac, so minus 4 e of x squared e of y squared must be less than or equal to 0, which means that e of xy all squared is less than or equal to e of x squared e of y squared. And then from this, if you take the square root on both sides, you just get your inequality. So I won't write that out, but I'll just put a QED sign there. All right. Okay, so the proof is not too bad. And now let's take a look at what this means Or how exactly does this imply the Cauchy-Schwarz that one might be familiar with? Well, okay, let's flip over actually. So, let's just write out the inequality for a second. So we have that the expected value of xy is less than or equal to the expected value of x squared, square root, the expected value of y squared, like so. Okay, now let's have a look at this. So we're going to define two events. So let's consider the probability space omega fp, where we just have omega just being some indices, some numbers from 1 to n. The events is just all the subsets, the power set, and the probability of I is just 1 over n, like so. So it's a uniform distribution. Okay? Now, we're going to define two events. So let's consider the two elements of our coordinate space Rn. So say we have x equal to x1 up until xn, and we have y is just given by y1 up until yn. Then we're going to define two different random variables. The first one is just given by x of I is defined to be xi, so it just picks out the ith coordinate. And very similarly, y of I is just picking out the ith coordinate here, so just picks out yi, like so. Okay, now what we're going to do is we're going to apply our probabilistic inequality to this scenario here, and we're going to see if the Cauchy-Schwarz inequality pops out, which hopefully it should. Okay, so let's just use the definition of expectation. So we have that the absolute value of the sum from I equals 1 to n of p of I, x of I, y of I is less than or equal to the square root of the sum from I equals 1 to n of p of I, x of I all squared times by the square root of the sum from I equals 1 to n of p of I, y of I all squared. Now, if we actually plug in what this means that, well, the probability of I is just 1 over n every time. So we just get that the absolute value of 1 over n, sum from I equals 1 to n of xi, yi is less than or equal to the square root of 1 over n times by the sum, not the square root, the sum from I equals 1 to n of xi squared times by the square root of 1 over n times by the sum from I equals 1 to n of yi squared. Like so. If you multiply by n on both sides and square both sides, what you get is you get that the sum from I equals 1 to n of xi, yi all squared is indeed less than or equal to the sum from I equals 1 to n of xi squared times by the sum from I equals 1 to n of yi squared, like so. And so indeed, you get the usual Cauchy-Schwarz inequality in Rn if you just apply the probability like this. And you can see if the integral version pops out using some continuous random variable. I mean, I'd be very surprised if it didn't pop out, but I haven't actually tried that myself. But yeah, I just thought this was a nice note, and there might be some deeper connections as to what's actually happening here, or some deeper interpretation, which I haven't given, but I'll leave you to look into it, and if you know some deeper reason for why this is happening, let me know in the comments. But until then, I'll see you soon. Goodbye.